Hello, this clip looks at the effect of haloalkanes on the environment because they do have an effect on the depletion of the ozone layer. So we're going to go through why and how that happens. So if you're using a textbook, this refers to page 229 to 231. And in the textbook they mention something called organohalogen compounds. Essentially, that is haloalkanes, but in other words, there may be more than one halogen atom substituted onto the alkyl carbon chain. So during the course of this clip, I'll be making some assumptions about what you've been learning already. We're going to assume that you've covered free radical substitution in alkanes, the chlorination of alkanes. That basically means homolytic fission of the chlorine-chlorine bond to make two chlorine radicals, because we're going to take that idea and apply it to organohalogen compounds. So we're also assuming that you understand the role of UV light in the creation of radicals. So we can take that idea and think about what might be happening up in the ozone layer. So if we draw a very badly drawn picture of the Earth, I'm not taking any responsibility for my map drawing skills, so I'm just going to create land masses like that. And let's make a nice big ocean in between them all. So we've got our atmosphere around the Earth, and we've got the Sun. Here. And let's give him a pair of shades. So the sun's beaming ultraviolet light in all directions. And within the ozone layer, it's in the stratosphere, you have a gas called ozone, which is actually O3. Now, you don't have to concern yourself with the bonding in ozone, as it's slightly complex, but what you do need to be able to think about is what might happen if oxygen is split into two radicals, or even if maybe chlorine from a haloalkane might be released as a radical. So, what we're going to do is create a new screen and talk about what happens chemically when a haloalkane might find its way up into the atmosphere. So if it's released as a gas, for example, maybe from a fridge or some refrigeration system or in the form of a CFC, then we can talk about what the CFCs do when they reach the ozone layer. So the thing to remember about CFCs, when I refer to CFCs, I'm talking about chlorofluorocarbons. So why are we worried about the ozone layer being depleted in the first place? Well, like I said before, we were talking about UV radiation creating radicals. UV radiation can also cause damage to the DNA in your skin, and if the DNA mutates, it can then lead to cancer in later life. So first of all, you get oxygen breaking up into two oxygen radicals if the oxygen is attacked by UV light. And this is a delicate balance that's sustained all the time in the ozone layer. So the problem is, if you get chlorofluorocarbons, for example, let's have a look at one. So we could have something like dichloro-difluoromethane. That would be an example of a CFC. What happens is these are also affected by ultraviolet radiation. So under the influence of UV light, what happens is that the carbon-chlorine bonds are more preferentially broken. So basically these bonds I'm circling are broken more easily. So what this means is you create chlorine radicals. Add these to the mix and a completely different set of reactions take place. Free radical based, but totally impossible to control. So the next slide, we'll have a look at the actual stages of the free radical reactions going to happen if chlorine radicals are introduced. You'll need to make sure you're familiar with initiation, propagation and termination from your previous work. So you may want to pause at this point and get your flashcards for free radical substitution, have a quick look at them before going any further. So basically what happens is we've got CF2Cl2 like this. The UV light will preferentially break the two carbon-chlorine bonds. It doesn't matter if there's some UV light hitting the carbon-fluorine bonds because the carbon-fluorine bonds have a higher bond enthalpy. So what this is going to lead to is CF2Cl. Notice the carbon-fluorine bonds are left alone. Your unpaired electron is on the carbon of the CF2Cl, and also you've got a Cl radical. Now the Cl radical goes off, or the CF2Cl radical can equally go off and cause a propagation. Or, if you've got some ozone nearby, the Cl dot radical can catalyze the breakdown of ozone. So that could be an alternative propagation step. So we can cancel the chlorine radicals and the chlorine ClO radicals to give us an overall equation. This tells us two things. The ozone is being depleted, and also that the chlorine radicals are behaving as a catalyst. So there are also some other ozone depleting reactions that occur naturally. So one might be from lightning. And this time it involves nitrogen oxide radicals. So again we can cancel out. We get rid of NO dot, NO2 dot. We end up with an overall equation here as well. However, in the greater scheme of things, because this is actually a naturally occurring process due to thunder and lightning, well, due to lightning strikes, it doesn't affect the ozone layer as much as the large volume release of CFCs. So for this reason, at the moment, CFCs have actually been banned by the Montreal Protocol. This was signed in 1979, and the idea was that zero production of CFCs would take place by the year 2000. In addition, we'd begin to get rid of CFCs and replace them slowly by HCFCs in some applications, hydrocarbon-fluorocarbons. HCFCs can be used in fire extinguishers. Even these have an effect on the ozone layer in the same way, but not quite to the same extent.